Okay, standard enthalpies of formation. This is a special type of molar enthalpy, and we use an F for formation. So there's your F, and it represents formation. So the standard enthalpy of formation is the energy associated with the formation of 1 mole of a substance from its elements in their standard states. So this is the definition for a standard enthalpy of formation. It's for 1 mole of product, so the coefficient in front of your product is 1, and the elements make it up. The elements are the reactants and in their standard states. So that means their states at room temperature, at 25 degrees. Alright, so for instance, the enthalpy of the molar enthalpy of formation of carbon dioxide is negative 393.5 kilojoules per mole. So the units, because these are a molar enthalpy, are always kilojoules per mole. So this means that 393.5 kilojoules of energy are released when carbon dioxide is formed from its elements in their standard states. So what does this look like in a chemical reaction? So the first thing you have to do is you write out your 1 mole of product. So I've got that here, CO2, and write out the reactants in their standard state. So carbon and oxygen make up carbon dioxide. So carbon in its standard state is a solid. Oxygen exists as O2. It's a diatomic element, and it's a gas at room temperature. And then you make sure it's balanced, same number of each atom on both sides. And then you can write your thermochemical equation by adding your enthalpy term. Notice that here it's kilojoules, not kilojoules per mole. Thermochemical equations don't have kilojoules per mole. All right, so then we have two different chemical reactions here. We've got the formation of liquid water from its elements hydrogen and oxygen, and the enthalpy change is negative 285.8 kilojoules. If we make water vapor, though, so steam, we release only 241.88 kilojoules for every mole of water vapor formed. So the difference in these two energies is in the kinetic energy of the particles. So here you're comparing the exact same substance, but in this state the particles are moving faster and they are so far apart that the intermolecular forces can't form. As this forms, as it cools down, this forms, and then intermolecular forces have reformed. So the molecules are now closer together, and then the difference in energy is the energy of motion that's been lost. So some of you might have high efficiency furnaces at home. Check. There'll be a tube, plastic or latex or vinyl tube, probably vinyl, tube coming from your furnace and either going to a drain or to your laundry tub. What happens there is as you're burning the natural gas, you're producing water vapor, and the furnace cools that water vapor down into liquid water that drains out of the tube, and you've actually used that difference in energy to further heat your house. So that's how a high efficiency furnace works. But you'll notice for all of these that we have only 1 mole of product. So let's do a couple of examples. Benzene, C6H6, liquid at room temperature. Carbon and hydrogen make up benzene. So to balance, we need 6 of these and 3 of these. All right, and then you will have in your appendix for your textbooks an enthalpy formation value table. So you can look up benzene in that table. And delta H is the molar enthalpy of formation of benzene is plus 49.1 kilojoules per mole. There's 1 mole in my reaction, so it's 41.9 kilojoules. All right, potassium chlorate. This is made up of potassium, chlorine, another diatomic element, and oxygen gas, diatomic element, and we make KClO3. So now we need to balance this. So normally you would balance this, you'd have to put a 3 here, a 2 here, and a 2 here. However, your enthalpy of formation reactions must have only 1 mole of product. So this is why we're allowed to balance with fractions in this unit. So 1 of these and a half of 1 of these and 3 halves of 1 of these makes 1 of these. So all I do is I go back and divide all of the coefficients by the coefficient in front of my product. So I divided everything by 2. And now you look up your enthalpy of formation. And the molar enthalpy of formation for this is negative. So the delta H is negative 397.7 kilojoules. So that's your thermochemical equation for the enthalpy of formation. Sorry, that's your enthalpy thermochemical equation for the formation of potassium chlorate from its elements. Okay, the next one is ethanol, and at room temperature, ethanol is a liquid. So we have the elements carbon, hydrogen, and oxygen. And we are going to make C2H5OH liquid. Okay, so we need to balance this, so we need 2 carbons, there's 6 hydrogens, so we need 3 H2s, and then there's only 1 oxygen, so we need a half of an O2, and then our molar enthalpy of formation is negative 277.6 kilojoules per mole. We have 1 mole, so our enthalpy change is a release of 277.6 kilojoules of energy. So the thermochemical equation for the formation of ethanol from its element is complete. One last one, magnesium hydroxide, Mg, solid, oxygen gas, hydrogen gas makes magnesium hydroxide. There's 1 magnesium, 2 oxygens, 2 hydrogens. And our enthalpy change is minus 924.5 kilojoules per mole. And we have 1 mole. So wow, quite a lot of heat is released when we form magnesium hydroxide from its elements. In fact, it's almost double making potassium chlorate from its elements. So there you go. That's how you write thermochemical equations for the formation of a product. So you have 1 mole of product, you have their elements as they exist at room temperature. You can only have 1 mole, so balancing gets a little tricky. And then you put in your energy term, and you find that in a table of standard molar enthalpies of formations. So there's something else that we can do with our enthalpies of formation. So we can write thermochemical equations for the formation of a substance, but we can also use them to find the enthalpy change for a reaction if we can't do the experiment, just like we did with Hess's law. So we have 2 ways to figure out the enthalpy change for a reaction. We can do an experiment in a calorimeter of some sort, or we can use Hess's law of heat summation, and now we have this option of using enthalpies of formation. So how do we do this? Well, we have a chemical equation. And in this chemical equation, we have these entities given by the capital letters, and the lowercase letters are their coefficients. So the enthalpy change for the whole reaction will be the sum of the enthalpy change for the products minus the sum of the enthalpy change for the reactants. So products enthalpy changes minus enthalpy change for the reactants. We can rewrite this as, because we know delta H is N delta HX, we can substitute in N times the enthalpy of formation of our products minus the sum of the enthalpy of formation of our reactants times the number of moles. So basically, for this reaction, take the moles of C times the molar enthalpy of C. We add to that the number of moles of D times the molar enthalpy of formation of D. So add this up. From that, we're going to subtract the sum of A times the molar enthalpy of formation of A plus B times the molar enthalpy of formation of B. So let's put that to practice. The thermite reaction is a pretty cool reaction. Well, it's very hot actually, but it's cool. And it's represented by this equation. Oh, I'm missing a 2. Now it's represented by this equation. So what we're going to do is we're going to look up the molar enthalpies of formation, and then we're going to solve this reaction. So our delta H for our reaction will be the sum of our delta H for the products minus the sum of the delta H of the reactants. So for our products, we've got 2 moles of Fe times the molar enthalpy of formation of Fe plus 1 mole of aluminum oxide times the molar enthalpy of formation of aluminum oxide so there's the sum of our products. From that we're going to subtract the sum of the enthalpies of our reactants. So we've got 2 moles of aluminum times the molar enthalpy of formation of aluminum plus 1 mole times the molar enthalpy of formation of iron 3 oxide. So if you go and look up this information in your data table, you're going to find an interesting thing. You're either going to see that there's no iron, no aluminum, or it's going to tell you that the value is 0. And that's because the enthalpy of formation of an element, so here we've got an element in its standard state, here we've got an element in its standard state. So at room temperature, aluminum is a solid, iron is a solid. So the value for the molar enthalpy of formation for them is defined as 0. So their delta HF is 0. For aluminum oxide, it is negative 1675.7 kilojoules per mole, and the molar enthalpy of iron 3 oxide is minus 824.2 kilojoules per mole. Okay, so we've got 2 moles times 0 kilojoules per mole plus 1 mole times negative 1675.7 kilojoules per mole minus 2 moles times 0 kilojoules per mole plus 1 mole times negative 824.2 kilojoules per mole. Okay, so it's important here to put these in because this is how your moles cancel and you go from kilojoules to mole to kilojoules, which is what the units are for your enthalpies of reaction. So we have, okay, 1675.7 kilojoules minus negative 824.2 kilojoules. So a minus of a negative means that's adding a positive. So our overall enthalpy change will be negative 851.5 kilojoules. So for this reaction, our enthalpy change for this reaction is 851.5 kilojoules of energy are released. So it's hot. Sometimes you might have to, you might be asked to make that into a molar enthalpy, and then you would just divide by how many moles of the species they want you to do it with respect to. So if they said with respect to aluminum oxide, it will be 851.5 kilojoules per mole, because the coefficient is 1 in front of aluminum oxide. Sometimes we're given the enthalpy of a reaction and we're asked to find the molar enthalpy of formation for one of the entities of the reaction. So it's really important as a student to slow down and read the question. I've had students solve and equate a problem solving for the enthalpy change for the reaction when really it asked for the enthalpy of formation. Okay, so here's an example. Ethane gas has a standard enthalpy of combustion of negative 1411 kilojoules per mole at SATP. So at 25 degrees Celsius, when you burn it, it releases 1,411 kilojoules of energy per mole of ethane that got burnt. What is the molar enthalpy of formation for ethane? So we're looking for delta HF of C2H2. So, sorry, C2H4. Not what we were just doing and finding the enthalpy change using the molar enthalpies of formation. So we need to solve for that. So our delta H for this reaction is 1,411 kilojoules per mole is released. We've got 1 mole currently in our chemical equation, but it's not balanced. So if I want to keep this as 1 mole, I need 2 moles of CO2. I need 2 moles of water. So I've got 4 oxygens, 6 oxygens, so 3 O2s. All right, now let's set it up. Delta H for the reaction is equal to the sum of the enthalpy changes for the products minus the sum of the enthalpy changes for the reactants. So negative 1411 kilojoules is equal to 2 moles of CO2 times the mole enthalpy of formation of CO2 plus 2 moles of H2O times the mole enthalpy of formation of H2O. Now this is liquid because this is happening at 25 degrees Celsius. So at room temperature, water is a liquid. So this is our products. From this we're going to subtract the reactants. And we have 1 mole of C2H2 and we have 3 moles times mole enthalpy of formation of O2. All right, so 2 moles times negative 393.5 kilojoules per mole plus 2 moles times negative 285.8 kilojoules per mole minus 1 mole times the molar enthalpy of formation of C2H2 plus 3 moles times 0. Now it's a good idea to put this enthalpy term in at the end. It's poor form to just drop it like you're ignoring it. So show that that is 0 before you're dropping it. Just good form. All right, so calculators are on. We know that this. Okay, so this first term is negative 787.0 kilojoules plus negative 571.6 kilojoules minus 1 mole times the molar enthalpy of formation of C2H. Oh, I don't know why I keep writing C2H2. It's C2H4. Okay. So work out the values for the product. This is equal to negative 1358.6 kilojoules minus 1 mole times the molar enthalpy of formation of C2H4. And this is all equal to negative 1411 kilojoules. All right, so now let's get to business. We're going to move our numbers around so that they are together. So I'm going to move this number to this side. As you move it to this side, it becomes positive. So negative 1411 plus 1358 is 52, negative 52.4 kilojoules. And that's equal to negative 1 mole times delta HF C2H4. Divide both sides by 1 mole, and it's a negative because we want our enthalpy of formation to be, the symbol to be positive. So delta H formation of C2H4 ethene is 52.4 kilojoules per mole. These ones cancel. So there we go. We have solved for an enthalpy of formation. So if you end up with a negative mole times the molar enthalpy, divide by the negative mole, and that will cancel the negative sign. So there you go. Oh, if you want to see something cool, not cool, it's pretty hot, watch this YouTube clip on the thermite reaction.